Hi everyone, and welcome to week 2 of lockdown 2 for higher physics. First of all, just want to say very well done to all of you who engaged with the work last week and managed to get on. I know it wasn't easy at the start of the week, and hopefully this week it'll be a wee bit easier on us. So well done. I think we've got nearly 100% engagement for the higher pupils, so really pleased to see that. This week's work is going to be about forces on charged particles. And just to make you aware where you're going to find the information, if you go into Files and then Particle and Waves Materials, what we're going to do is, rather than have it set up as week 1, week 2, we're just going to set up all the work based on the topic that we're learning about. So last week's work will be in the standard model, and this week's going to be on forces on charged particles. You can find the checklist still in the main Files tab, but the resources are going to be in here. So what I'm going to do just now is just briefly talk you through what the work for this week's going to be, and then cover very briefly some of the content. So don't expect this to be everything you need to know about it, but just at least introduce you to some of the key areas and concepts. So for this week, what we're going to ask you to do is very similar format to last week. Our title is Forces on Charged Particles, and what we've got is a list of tasks that are going to help you to learn what you need to know about forces on charged particles. What you'll find is the first couple, you will find that the materials are a bit repetitive, but that's the point, is that by completing different various tasks, you can consolidate what it is you need to know. So the first one, there's a good link that some teachers have made. If you click into that, it's got some videos about forces on charged particles, and then it's also got a quiz that you can attempt, and it self-marks. Now, we won't see those answers, so feel free just to work your way through that and see how you get on after watching the videos. Then, as usual, we're going to get you to read through pages 14 to 18 of your notes booklets, and that's got all the theory that you need to know for this topic. BBC Bite Size have also got notes. Again, it'll be similar to what your notes are, but it's just another format. It might be easier to go onto that on a device rather than try and read your notes. Again, it's up to you. We've also got a PowerPoint that we would normally be using if we were in class and we were teaching you this. The PowerPoint's for a much bigger section, so it's only slides 1 to 14 that is relevant to you, and I'll go through the PowerPoint during this video to highlight some key areas. So you can have a look at that. We're then going to ask you to make your own note. So again, similar to being in class, we talk about the information, we learn the key concepts, and then we would normally make a note on it. We've given you some bullet points here of what you should have included in your note, just to make sure that it's got everything that you need to know. And again, as usual, after we write the note, we go on to problems. So quite a lot of problems available for this unit, not to put you off, but the more practice you get, the better you're going to be at them. So they're on pages 10 and 11, 12, 20 and 21. And 20 and 21 are the past paper questions. So that's in Particles and Waves question book 1. And you should also be able to check your solutions, and the answers are on pages 50 and 52 for that. So as usual, work your way through, making sure to check your working as you go. Again, we're going to ask you to upload all your work into the assignments tabs, just so we can have a look and see how you're getting on. If you're making any mistakes, we can hopefully give you feedback before we get too far on. And then again, as usual, the last thing we're going to get you to do is to complete this week's assignment, and that'll be available Wednesday of this week for completion, as usual, by midnight on Sunday. So what's this week about then? So our learning intention is we're learning about forces on charged particles, and our success criteria is that you can define what is meant by an electric field, sketch field lines for isolated charges, system of 2-point charges and uniform fields, determine the direction of movement of charges in an electric field, define voltage in terms of work done and charge, And then Old Faithful, solve problems, which is our equation work, involving charge, mass, speed and energy of a charged particle in an electric field. So it does seem a lot, it is a lot. Bear in mind this is 5 periods worth of work. We would normally have split this up a little bit more, so try not to be overwhelmed with it and just take each success criteria at a time. Like I say, there will be equations this week, and that's when we see the solve problem success criteria, but hopefully it'll be a bit of a relief to see that charge, mass, speed and energy are all quantities we've met before, so nothing new in terms of quantities. Okay, so just to sort of finish up the video, like I say, I'm just going to talk you through the PowerPoint. I'm not going to go through every single thing because I'm sure you'll just get bored and switch this video off halfway through. But like I say, I'm just going to highlight some of the things that you need to know and pick them out. So you will have this PowerPoint, so I'll go through it quite quick. So electric fields, particles and fields, we're not going to be talking about particle accelerators this week, that's for next week. So starting off, a little bit of revision about charges. So hopefully we can all remember from National 5, there are 2 types of charge, electric charge, and they are positive and negative. And a reminder that charged particles, charges that are alike, will repel, so positive, positive, negative, negative, and opposite charges attract. Okay, so fields. So the first thing is, when we talk about any sort of field in physics, it is normally we're talking about an area around something where something else will experience a force. Now, in terms of the electric field, we're talking about the area where a charge will experience a force. That's what we mean by an electric field. So if we've got our 2 types of charge, positive and negative, in an electric field, they will experience a force. Now, one of the first success criteria is that you can define an electric field and then sketch field lines was our second one. And that's exactly what these diagrams are that we're looking at just now are. They are field lines. So these black lines with the arrows on it are our electric field lines. So it's important that you're able to draw them. So again, you'll watch some videos on this, so you will be more familiar, hopefully, over the coming sort of days, but that's what you need to be able to draw. And it tells you here that the arrows would always go in the direction that a positive charge would move. So if you took a positive charge next to a positive charge, it would move away from them, and that's why the arrows are pointing out the way. And if you took a positive charge to a negative charge, it would move towards it and the arrows are pointing in. A couple of things to note when you're drawing your charges, because it is one of the things that you're expected to do. So if I had a charge here and it was a positive charge, when you're drawing your field lines, make sure that they touch the charge. Okay, you don't want a field line like that, definitely not like that, but you want to make sure that they touch the charge. That's one of the things that the examiner will look for. Now, there's no rule on how many lines you have to draw, but the rule is that they have to be equally spaced apart. Okay, this is normally the one that we go for, where you kind of do a cross and then a diagonal, and that's probably the easiest way to go about it. But you may see diagrams with more lines in it, and they are perfectly okay as well. But again, as long as you're consistent and you have them in all directions so that they're equally spaced apart. The other thing you must include is an arrow. The field lines you need to have, well, mine aren't straight lines, but hopefully if you're drawing it, you can use a ruler. But you need to draw your arrows as well. And your arrows have to show where a positive charge would travel. Okay, so make sure they're on every one of them. Now again, what that just means is that if I were to take a positive charge and place it here, this is the direction it would go in. So that's what our field lines are representing. Now that is when we have isolated charges, meaning that they're on their own. But obviously that's not always going to be the case. If we have more than one charge next to each other, and at higher level we only deal with 2, then you have to draw the lines like this, again representing the direction that a positive charge would travel in. Okay. A uniform field is when we produce an electric field where it's constant throughout, and that's represented by these parallel plates and the lines equal distances from each other. And how we achieve that is oppositely charged parallel plates. And again, you'll spend a bit more time reading through that. Okay, so charges in an electric field, like I say, if we have a charge in an electric field, it will experience a force. If it experiences a force, it means that it will move, work is being done, and this creates a current. One of the things you need to be able to do as well is define the volt, or define what is meant by voltage. An equation that you did at National 5 level, not in a huge amount of detail, is this one here. So it's our work done equals Q times V. And that's really our equation for defining what voltage is. If we rearrange that, if we rearrange our equation for work done in an electric field, so we have voltage becomes E over Q, and that tells us that it's the energy transferred to each coulomb of charge. Okay, so remember your equations always tell you your definitions. So voltage means the energy transferred to each coulomb of charge. Or if 1 joule of energy is transferred to 1 coulomb of charge, that's the same as 1 volt. Okay, so you need to be able to define or state that definition of what is meant by voltage. Okay, so getting on to the movement of particles within fields now. A way to think about it is it is similar to gravity and gravitational fields. So if you're wanting to lift something off the ground, you have to do work because you're acting against gravity. And the same thing happens in an electric field. So if you want to move the charge, in this case at the right hand side here, if you're wanting to move the charge against the electric field, then work has to be done. You have to provide it with energy to do it. Okay, now what it also means is with the gravitational fields, if we hold up something high and drop it, it will accelerate towards the ground because of gravity. In an electric field, it will accelerate towards the oppositely charged plate because of the electric field. So you've still got that acceleration. Now, similarly with gravitational fields, we talk about that work being done, that the potential energy is then converted to kinetic energy, which you can calculate by doing a half mv squared. The equation still works for a half mv squared if we're talking about the charged particle. So if we talk about that particle moving in the field, we say that work has been done, and that work done is QV, but if we talk about the conservation of energy, then that work done is saying it's been converted from electrical potential energy to kinetic energy, which is a half mv squared. Okay, now I went through that really quickly, so feel free to rewind and listen again. But essentially what happens is, we like to talk about things in terms of equations, is that we get this equation here. Because what we're saying is that QV is the work done by the field and on the particle, and it's been transferred into kinetic energy, which is a half mv squared. Okay, now the good thing about that is that these are all fairly easily measurable quantities. Okay, so charge, voltage, mass and velocity of our particles. So if we know, as usual with all equations, if we know all of them bar one, we can work out the unknown. Now, it isn't the nicest looking equation because it is quite a lot of unknowns, but again, we just treat it like any other equation and we substitute in, then rearrange to get our final answer. So most of the problems are going to revolve around this, so you'll have plenty of practice. The things to bear in mind that in this equation, V is the only thing that's squared, so be careful with that. Now, if we look at this diagram here, This is kind of a classic example of if you fire a particle into an electric field with a horizontal velocity, what will happen is that the field will deflect it. So it wants to keep going straight forward, but in this case, because it's a negative particle, it's going to be accelerated down towards the positive plate caused by the electric field. Now, hopefully, you're thinking to yourself now, that's a bit like projectiles, that it wants to keep going straight, but there's a force that's causing it to accelerate down, and in this case down. And it's very, very similar to projectiles. You've got the same situation going on. The only thing I would say is projectiles, we always talk about it being accelerated down, because in a gravitational field, that's the way the acceleration will always act. However, with an electric field, if this were a positive charge, it would be accelerated up. So it's not as simple as always the one way. It depends on the charge and the direction of the electric field. And another example here showing what's happening to the force as we go through a uniform field. And again, you can see the similarities here with projectiles. Okay, and that is up to slide 14. So that's all the information for charges in an electric field. So again, just to highlight, that was very, very quickly going through the concepts for this week. I don't expect you all to be experts after that. But again, you've got this link here with another video. You've got your booklets, bite-sized, and lots of different places to find this information. What I would say is when you're making your own note, if there is any questions at that point, please ask us to make sure that your notes are accurate and you're not writing down anything that would be counted as wrong physics. We are going to have another 2 sessions this week for drop-in. We'll confirm the times today, and hopefully we can see a bit more of you this week. But again, you don't feel you have to, but if you do just want to come on and ask a quick question or just listen in, then that would be great, and it would be great to touch base with some of you.